All right, 6.2 and the last lecture video for this entire term. And as it turns out to be a very short video for y'all to in this part at least. So 6.2, we're going to very briefly talk about some characterization of a planar graph. Remember, whenever we say that we characterize a graph or some class of graphs, that is, we're finding equivalent definitions. Or in other words, we're finding these things where I'm a planar graph if and only if this occurs, or if and only if this other thing occurs. So some quick definitions for this video. A subdivision. A subdivision of a graph G is a graph obtained by replacing an edge, or edges, with a pairwise internally disjoint paths, or paths. So if I'm replacing a single edge, then I don't really need to worry about the pairwise internally disjoint part. But otherwise, I can, if I'm replacing multiple edges, I need to make sure that they're internally disjoint. And just for a common terminology, when I replace an edge with a path, we say that we subdivide the edge. So here I have a very quick example. On the left I have G, and I labeled the edges E1 and E2. Notice on the right, it looks like I replaced E1 with a P4 path, that is the path with 4 vertices. And I replaced E2 and then subdivided it into P2, that is the path with 2 vertices. So this is what we call a subdivision. So what can I do with these subdivisions, and what do they have to do with a planar graph? One thing that I want you to notice about the subdivision is that even though that these are no longer the same graphs, they sort of still have the same shape, more or less. It just looks like, again, I replaced an edge with a path. So, theorem 6.2.1, and forgive me if I mispronounce this if you know the correct pronunciation, Kuratowski. This is from 1930. A graph is planar if and only if it does not contain a subdivision of K5 or K33. Remember that K5 and K33, these were those two graphs that are not planar. If I see either of those two graphs, I know that I'm not dealing with a planar graph. In fact, if I have a subdivision, a subgraph, or what we'll hear about in a second, a minor, that is K5 or K33, then we know we are not planar. So that's our first theorem here. And this theorem actually, again, is one of those theorems that actually takes a very long time to prove. So we won't be going too far into it. In particular, the one that's a little bit more difficult to prove is that if I am planar, then I do not contain the subdivision. Well, or the other direction, I mean. All right, so the next thing I want to introduce is a minor. A graph H is a minor of a graph G if a copy of H can be obtained from G by deleting or contracting edges of G. So in other words, another way that you can think of this is that a minor is either a subgraph of G or a subdivision of G. Deletion implies that we have a subgraph. Contraction is where the subdivision comes into. So as a very quick example here I have our famous Peterson graph. It looks like I have a pentagon with a star inscribed in the middle, and then the star and the 5 cycle on the outside are connected by single edges. If I consider these edges between my star and my outer 5 cycle, so what I have here, let's see if I can draw this actually. Pin, so this edge, this edge, this edge, this edge, and this edge. If I contract those edges, it looks like I just pull these two vertices together and make it into a single vertex for each one, then I actually end up exactly with K5, the complete graph. So that means the Peterson graph has a K5 minor formed by contracting. This also tells me that since I have this K5 minor, that my Peterson graph is not planar. And that's a modification of our previous theorem. So that's the main thing I want y'all to pull from this very short video. If I can find a K5 or a K33 subgraph, or minor to be exact, then I am not planar. And if I am planar, then I should be able to redraw this some type of way such that no two edges cross each other. All right, so besides that, that is all for this video. Again, very short video, but I really wanted to introduce this very important characterization of my planar graphs.